In the previous video, I made this bulk labeling interface, which is effectively a scatter chart that you're able to make selections in. And if you have a scatter chart that uses sentence transformers combined with UMAP, then this can be a convenient way to really quickly detect some clusters and just immediately associate a label with it. That technique is great, but it does come with a couple of downsides. A big one is that it can be quite slow. After all, text goes in, we gotta calculate these heavy embeddings, and then we gotta do UMAP, which is also a bunch of compute. And that can drag you down. Sometimes you just want to get started right away. There is another issue though, and that is with the interface. In the end, the labels that we're making using this quick selection approach can actually lead to a couple of bad labels to seep in. We're not looking at each individual item, we're really just assuming that everything in the cluster is part of one label. So in this video, we're going to make an alternative that tries to address both issues. We are definitely going to be using embeddings again, but we're going to take a very specific kind of embedding that is a lot cheaper to calculate, but is still relatively accurate. After that, we're also going to be making a much simpler interface that uses keyboard shortcuts to do fast annotation for us. But before diving deeper, let's first discuss a little bit of theory, just so we understand why there's this other embedding technique at our disposal. So let's do just enough theory to get the point across in this one. What I've drawn over here is roughly, and I need to emphasize, roughly, what is happening inside of a BERT-like model. We have some tokens of text that go in at the beginning of the system. Then for each token, we've got some sort of a numeric representation that's learned during training. And that goes into a transformer block, so to say. Now, inside of this transformer block, all these embeddings are being compared with one another, and that is being used to maybe add context, such that the embeddings that go out here just are a little bit quote-unquote better. Now note that this is not just happening once. Usually, a lot of these transformer layers are clicked together in sequence. But the main observation, like the main point that really matters, is that we do a lot of compute, but then at the end over here, we've got these embeddings that map to these tokens, and because we're doing all of this compute, we can add a little bit of context. And that means that if I have a sentence like bank on the river, and another sentence like money on the bank, that then the embedding for the word bank in this sentence is different than the embedding for the word bank in this sentence, simply because it's surrounded by different tokens. All these transformer architectures and all the compute that we're doing is hopefully going to give us a better embedding, something that's just a little bit more contextualized. So I'm definitely glancing over a lot of details here, but this is an intuition that I do think is somewhat accurate. The reason why we do all of this extra compute is that we're able to give ourselves better embeddings with more context for the sentence that we're in. So a very natural next question is, like, what can we do such that we might not need to use that much compute? And the big thinking is that, well, what we could also do is we could say, well, let's just loop over all these tokens that some pre-trained model has, and let's pass the token into all of these transformers. And then, you know what? For this one token over here, we are just going to take this one representation that comes out all the way at the end. And from there on, we are basically going to keep track of a dictionary. If this token appears, we are just directly going to map that to that vector. We're basically using a BERT model to give us a word vector. And we can do that not just for that first token, we can do that for all of these different tokens. We're really just using BERT here as a method to produce word embeddings. And the benefit of doing this is that you might still be able to get a pretty interesting representation of a word, but you're simply going to omit doing all of this extra calculation, and that saves up a whole lot of compute. We're going to acknowledge that the representation for all of these different tokens, that is going to be quote-unquote worse, because you're not able to compare to all the tokens in a sentence, so to say, but maybe this will be fine. If we have embeddings that are maybe 100 to 1,000 times faster to compute, maybe it's fine if the embeddings are slightly worse. And another part of the intuition here, by the way, is that if we are going to be calculating these embeddings for all of these words in a sentence, well, we still want to have an embedding for the entire sentence. So what we can also just do is just take the sum or the mean of all of these embeddings together, and that is going to give us sort of the average embedding of the entire sentence. And even if there are words in there that are overlapping, you can still imagine that the fact that the word river appears over here and the word money that appears over here, that we still have a separate embedding that might actually have different properties as far as similarity is concerned. So the name of the game here is approximation. We are really going to do very aggressive distillation, you could say. And there's a library that I've been a fan of for a while now called model2vec that comes with a suite of tools to facilitate just this. It is integrated with sentence transformers, but you can also use this library directly. And if you do that, then you don't even need PyTorch around. You actually get a very lightweight virtual environment too. So this is what I'll be using under the hood. It's this trick, it's this technique, and this is going to give us embeddings that are just a whole lot quicker. So just to reiterate, what I can do is I can come up with some sort of a sentence under the hood that is going to be split up into separate tokens. And the way that we're going to get to those tokens is similar to how a BERT model might do it. But then we are not going to pass that to BERT. We're really just going to be doing a lookup for all of the word vectors, so to say. And then if I want to get my final embedding of the sentence, then I can do some sort of a pooling. Let's assume the sum for now, but I believe they also do something with the mean. That is going to give me my sentence embedding. This is going to be a whole lot quicker. I cannot stress this enough. This is going to be super quick. But then what? What we could do is we could take all those embeddings and pass them through UMAP just like before. But instead, I'm going to omit that because there's something else that I can do too. If I have my database of sentences, then hopefully it's clear that with this technique, we can turn that into a quote-unquote database of embeddings. And from here, what I can do is I can also still come up with some sort of a query. I can come up with a embedding for that query using the exact same approach as before. And what I could go ahead and do is just retrieve the top 100 most similar. The benefit of doing this is that by not going for that pretty chart, and by just sticking to similar items, I can also come up with a much simpler user interface that allows me to just take every single item that appears over here and to just attach a label to that directly. As a human in the loop, I will actually see every single example, which also means that the probability of getting bad labels in because I'm selecting a big cluster also becomes a lot smaller. And also note that if I do this in a clever way, then I can add buttons here that also come with keyboard shortcuts. So I will still have an interface that's nice and interactive in the sense that I can add a query, maybe annotate 20 examples or so, add a new query, and then at the end of maybe a 5-minute session, I should still have very relevant labels at my disposal that I can use for a first machine learning model. In a lot of ways, this can still be seen as a variation of bulk labeling because I'm relying on embeddings to really save me a lot of time. I don't have to go through all of my examples. I can really just focus in on the few examples that I'm really interested in. But this is something that is also live right now. So let's quickly show you how this works, and then I can also show you how this is made under the hood. So here is our fast labeling demo. It is on Hugging Face, so you can try it out yourself if you want to. And just like before, you can upload a CSV file with a text column, and everything will work as it should. But for demo purposes, I'm just going to use the same ringtone dataset that I had before. This is a dataset that is all about text messages, and some of these text messages are spammy, and we're interested in labeling those. Now, to fetch similar items, let's go with this sentence over here. You will get a free ringtone. That sounds kind of spammy, right? Could be a good place to start. And when I hit submit, a little interface pops up down below over here. Now, just like before, what I can do is I can attach a positive class name. So I can call that clean, and there's a negative one. Let's call that spam. This is definitely kind of nice because now I have a right name. And then I can go through some examples. So right now here it says current example, ringtone club, get the UK singles chart on your mobile each week, and choose any top quality ringtone. Yeah, that definitely sounds kind of spammy to me. Then the next one appears. Yeah, that also looks a bit spammy. Also spammy. This is also spammy. So a bunch of spam in here, no surprises there. One thing you'll notice though is when I hover over a button here that you then also see a shortcut appear. In Marimo, you can actually configure buttons to hold some shortcuts. So if I wanted to be quick about it, I can also hold Control K or Control L or Control U. And shortcuts like this can actually save you a whole lot of time as well. So I can actually smash my keyboard, so to say, and yeah, no need for a mouse. That's also kind of nice. If I were then to scroll at the bottom over here, you're going to see this table that has all the annotations that I've got so far. You will also notice that there's a little download button at the bottom, and I can also change the text here as well. So if I were to change the reference sentence to "at what time will you be home," then also the example that appears down below over here updates, and again I can say that this is probably clean as well. One thing to observe here, by the way, notice how we're not waiting for embeddings. Generating all these embeddings is pretty much instantaneous, and that's the really cool thing about it. The model2vec library that we're using here really can be 100 to 1,000 times quicker, and just from eyeballing this, I do think it's fair to say that if you're just dealing with sentences, the similarity between a query and what you get back seems to work out quite nicely. This approximation might not work once you're dealing with longer and longer pieces of text, but as a, hey, I just want to get some training data real quick kind of a vantage point, I do think there's a lot to like about this interface as well. Before wrapping up though, I do want to maybe mention a few things that I'm using under the hood from Marimo to actually get this interface working. One part of the functionality is this keyboard shortcut parameter that you can add to this UI button class in Marimo. It's something that a lot of people don't know about, so I figured I'd at least mention it. You can just write down something like control and then -L. And that's everything you need to do to allow for the Control-L shortcut. Be a little bit careful here though. If you were to actually add letters here, odds are that you're not able to type text properly anymore because it can really override the normal behavior if you're not careful. And there's also a couple of browser shortcuts that you probably don't want to override here. But Control-L definitely felt fine. And then finally, you will notice that this is a stateful notebook. I'm going to have to keep track of all the examples that you've labeled. But I did notice that there's also this middle ground that you can take. Normally, whenever you're dealing with state in Marimo, you would use the mo state functionality. This will give you a function that allows you to set and allows you to get the state. And although that's very flexible, in this particular case, I noticed that I could also use a generator. And this was quite convenient in this particular case. Whenever I have a new query, I also have a new list of similar embeddings. And I want to take the top 100 of those embeddings, and then I basically have a pile that I want to go through. And after I've annotated the first example, I can just grab it off the pile and never refer to it again. And a generator is actually very well equipped to do that. You can just call next on it, it will grab the next item. Now note, for the current example, you do need a state object, but it is nice that you can use a generator as a little bit of middle ground to take care of that pile of items to go through. It's just a little thing that makes it a little bit easier to reason about the code here. So there you have it. If you're interested in doing some light annotation, this app is live and definitely feel free to use it. If you're curious on how this was built, you can also check out the source code from Hugging Face. And I guess the main thing I want to say at this point is thanks for making it to the end of this video, and I will see you in the next one. If you want to see more videos like this, by the way, do hit subscribe.